Hello, everyone. So I'm Geoffroy Hautier. I'm at Rice University. And so I'm going to talk about, this is a purely a computationally driven search for materials. In the context here would be to actually search not for material, but quantum defects for quantum information science. So I'll make a general point about the last 10 years have really seen a lot of usage of high throughput computing, where you compute properties of materials in database, band structures, all kinds of things you can compute with first principle computation. And usually when you look for materials that align a lot of different properties, and you can kind of screen out and lower the range of possibilities. These are a few successes, on my work, but there's been a lot of groups working in this where we really went for prediction from the computer to actually realization of a new material with interesting properties and behavior. And also, part of that is like the amount of data that has been generated. One of the efforts being the Materials Project, which you might have used. There's actually, Materials Project has already 400,000 users. So it's really changing the way we used to look at materials, and we used to look at materials properties with computation. But I'm going to make a point that one of the things that has been not as studied is the defects in the material. Most of these things are bulk properties like band gaps or elastic constant, etc. And if you look, there are plenty of examples where the properties are heavily driven by defects in material. This is known. So the question, and some of the thing we're trying to tackle in my group, is can you bring this type of technique, high throughput computing, including the AI and ML opportunity that is on that with point defects? And the example, in terms of application, I'm going to take, because it's a quantum materials workshop, is the use of defects for quantum information science. And quantum information science would be including computing, sensing, communication, and there are plenty of platforms, and defects or color centers in semiconductors, one of these platforms that have strengths and weaknesses compared to all these different platforms. But what would you do with these defects in material? What can you do? And why do you need them? Basically, you can use them as qubits. And this is the simplest picture I can imagine of one of these defects. This can be much more complicated. But think about a defect that is paramagnetic, where you have a spin down and spin up and spin down state. You can think that's a qubit. The nice thing is that if you have a qubit, you can do all kinds of quantum operation, preparing, entanglement, etc. And these defects that are color center, one of the really nice things is you can control them optically. And there's a lot of things with detectors and laser you can do. And so typically you will search you want defects that you can excite. Let's say you're applying a magnetic field on a doublet, you have two states, and then you can excite preferentially certain spins. And if you do cycles like that, you can prepare actually a defect in a certain spin state. What can you do after? You can control for instance, you can prepare it in a superposition state. So if you started with, let's say, spin up, you can kind of do with a microwave then pulse, kind of prepare a superposition state. And then you can read back what happened if you've done quantum operation, what happened through basically looking at what frequency would excite the defect. So this is a very simple picture of what you like to have in these defects and what you can do. And they're actually very nice proof of principles. This is a paper from 2 years ago where they entangled like spins by 30 kilometers, I think it's 30 kilometers, away from each other through optical fibers. And quantum sensing is also a big approach and very useful case of this. You can use these defects to do sensing. Lucas showed some NV magnetometry. This is actually arguably the most usage of quantum information science is the NV magnetometer that you can actually use for quantum sensing nowadays. So if you look, what's the status of these defects? It's a little bit like materials, you have plenty of them. Some of them that are good for certain things, some of them are bad for certain things, and you're happy with none of them, actually, in terms of all the properties you like. And there are hosts you can pick, diamond, silicon, TMDs, and you have different defects, the NV in diamond being the most famous one, but none are perfect. And so what we're trying to do is searching for the perfect imperfection in some sense. We're trying to search for the perfect quantum defect. Is there anything out there that could be better? And it's interesting, like most of these defects, like say the NV in diamond is just there. There's plenty of nitrogen and vacancies in diamond, and they just form. And this never be, we just found a defect and try to find a usage of that for that defect. And I would argue that the vast majority of defects we use nowadays in the quantum information science are in this case, in this category of defects. What we're trying to do is, can you reverse this process and think about what we need for the defect and search among the possibilities and then target synthesis of these defects? So we've set up a high-throughput screening approach for quantum defects where we start with, in this case, it's 2 hosts. I mean, you could use that for any other host you're interested in. This is our collaborators who are working on tungsten sulfide and silicon, and there are good reasons to work with this host. But then you can use first principle computation to compute things like, do you have a paramagnetic defect? Is it going to emit in the right wavelength? Is it going to be bright? Is it going to be an efficient defect? Are you going to lose a lot of things in the phonon sidebands? Et cetera, et cetera. And I'm not going to go in detail here, but there's a lot of work in picking the right level of theory at the right time, and also a lot of work actually in automating all these computation. But we're really at the point that we can basically press a button and compute defect properties for like 1,000 defects pretty easily. So by any means, this is not all the properties you like, but at the very least, what you'd like to have is within your bandgap, you'd like to have defect states you can excite, and you'd like to have a paramagnetic defect. You'd like to have something with a spin that you can play with, and you like that distance between levels to be in a wavelength that is something you can work with, visible, telecom, and you want that transition to be bright. I mean, these are some requirements that you do, and we started with tungsten sulfide, wondering, can we look at all the defects in tungsten sulfide and find maybe the best one or the best ones that would work? And this is the result of such screening. All of these dots are basically a defect. The entire periodic table put as a simple defect either on tungsten or sulfur. And you can see the excitation energy at a certain level of theory and transition dipole moment. So you want something bright, so you want that to be high, and you want something to be pretty high here also, because if you're in that regime, you're going to have things that emit in the mid-infrared and things like that. And this is not good for fibers. This is not good for detectors. This is very difficult technologically. So you like to be here. So if you look at all of these and you start browsing and say, okay, what are they interesting? You also want something that is not a singlet. So you want something with a spin you can play with. And if you put all these constraints, you end up with identifying cobalt on sulfur. And I would argue, honestly, I mean, no level of, at least my chemical intuition, would have suggested to put cobalt on the sulfur side in tungsten sulfide to have a 2-level system that would be paramagnetic. So this is a level of screening. Then you can kind of, okay, this is actually a great project because we have experimentalists in the project in the same funding. And so we went to the experimentalist, said, okay, looks interesting. But talking about synthesis, this is a workshop about synthesis. Yeah.
So this is in WS2?
Yeah. Yeah. So talking about synthesis, putting cobalt on the sulfur side, that sounds not the most easy thing to do. And this is a synthesis challenge. And so I agree with that. I recognize that. But that's interesting sometimes to see the computer doesn't have this bias. Computers just put things in there, and then you have ideas. Okay? So this is going to be difficult to make. Can we make it? It depends the way you make it. So I have this very nice and colleague, Alexander Weber-Bajani, who does a lot of STM, and he's pretty good at controlling vacancies in tungsten sulfide. That's pretty easy to make. But then he had this idea of saying, can we use something and make vacancies and evaporate cobalt in the STM? And actually something also he needed to do is to do pulses to actually make the cobalt diffuse. And then at the end, I mean, this is not scalable. This is something where you can be careful, and you can find some defect that will be filled with cobalt. So it's a little bit like playing mini golf with metals which is crazy. I mean, this is of course months and months of work. I mean, this is very challenging, but we managed to do it. And the beauty of the STM is you really have a surface, and then you can go probe, and you can be convinced there's cobalt in there. But you can also you can actually start looking at the electronic structure. And remember, what we want is this 2-level system. And if you look actually at the experimental results, we see 2-level systems in the bandgap. And we can even compare, which is for theorists, this is amazing. It's rare that you can look at the wave function. Yeah.
So maybe you have the two-level systems, but how do you control the number of electrons? I mean, the oxidation
So,
state.
yeah, so we have some sense of that. I mean, do you have this slide here? I don't have this slide here. We do also like, we do computational analysis of the different charge states that you could have. It is a good defect in the sense that the charge state that we want, which I believe is the neutral one, is actually pretty stable in the entire.
Something about the electron filling that makes sense, though?
Yeah. Yeah, these things behave weirdly also. Putting a cobalt on the sulfur, it's like, no, but the number of electrons, we can look at that with, I mean, it's like you can do defect computation with different charge states. We're always worried about that. You're right. You could be in a situation where you predict a defect, it looks great. Like I want some defect, but the charge state is not stable. So you can never stabilize that thing. We're very worried about that. Among our screening, this is actually the first thing we look at, is would there be a range of Fermi level where reasonably you could have this specific charge state that's there. But the STS doesn't tell you that.
Do you remember if it was near the valence band or the conduction band?
I have this slide. I mean, I can maybe at the end show you. I might have a backup slide actually on that, or I can show you after. Yeah, I can show you.
Because once you start the process, there's so many other criteria.
Yeah, but charge stability is one of the first criteria we look at. We really don't want to discover something that is a beautiful electronic structure, but in terms of charge, this does not be a stable charge state. You don't want that, and that it happens. It happens. So we're pretty convinced we can stabilize it. The challenge here now is it's not that actually. The challenge is to optically try to address it. This is only electronic. I mean, at the end, we think these are good evidence that there are going to be optical transitions. We haven't proven that. The problem is there's not enough cobalt to make optical measurements. So Alex is actually working on doing in situ optical measurements now, which it's its own challenge, but I mean, making good progress on that. So we're also working on something talking about synthesis. These STM pools and evaporation is kind of annoying because the evaporation limits you on terms of the type of metals you play with. We're kind of lucky that you could do the cobalt. But one thing he's been doing recently, and this is unpublished but pretty exciting, is creating vacancies again, but then you come with a molecule. And you have some complex of molecule. This is really just putting, I mean, why europium? Basically, that was what we had as a molecule. And there was
like ALD.
Yeah, exactly. And they had a good complex there that we could use. And then they showed that you can do that, do some heat treatment, and create the defects through molecular approach, which has tons of advantage, no evaporation. You don't need to do this STM pulse. And so this is really very preliminary result. These are vacancies, but then there's a vacancy that doesn't look like a vacancy. There's one that's a little different. And so the hypothesis is like maybe europium got there. And so far the computational result, I'm not saying it's an interesting defect for quantum information science. This is just to show the proof of principle. From our theory, we think these states that they see here are actually D states of the europium. You don't see F state, they're much lower in this case, but we think at least we have getting evidence that you can make things like that also, which is something we can explore for cobalt, but other ones as well. Okay, so that's tungsten sulfide with a lot of synthesis challenges, but that's the beauty of like theory and working with folks that can synthesize pretty exotic things. I'm going to move to something that's from the most exotic to the most established host, which is silicon. And it's pretty easy to explain why you'd like to have these defects in silicon. Because if you have these defects in silicon, you can basically use a multi-billion dollar industry of CMOS, nanophotonics, all these things. Everything is easier in silicon. And so there is a growing community actually developing these defects in silicon and trying to make things with silicon. The competitor there would be diamond, but silicon is much easier to deal with than diamond. So there are more and more papers, especially on that defect, which is called the T-center, carbon-carbon hydrogen on silicon. It's kind of a complex defect. That one is paramagnetic, emits in the telecom, And people have shown very interesting, and I'll get back to that, quantum operation. The big challenge with silicon is, remember this picture of 2 levels in the bandgap, and you don't want to be in the mid-infrared, and you cannot be too high either. So you kind of have a very small window in which you need to design your defect. So you like to be exactly within the bandgap of silicon, which is challenging to find the right defect. And this is actually a little bit why, like, for a very long time, silicon has been totally dismissed from this community. People like to work with diamond, 5 eV bandgap. But it's really changing a little bit recently with some of the result. You can do really nice thing with silicon. This is work from in collaboration with my colleague Alp Sipaegil. This is basically showing that you can integrate. This is one defect. This is called the G center. This has no spin, but here it doesn't matter. This is one defect in a silicon waveguide that you can address, and you can pulse photons, and you can see if you can make indistinguishable photons. So this is a nice thing you can do. More recently, playing with the spin now, Alp showed that you can entangle basically nuclei of silicon-29 and hydrogen from the defect, and silicon-29 just next door. And through this spin-photon interface, you can kind of control these 2 nuclei. Why nuclei have a longer coherence lifetime? So you can kind of control through light this T center, and control through hyperfine coupling, you can control these nuclei. It is pretty crazy that you can do that to this atomic level control. But that's the beauty of silicon also. Easy to process and high quality samples. So you can ask, okay, what about the defects in silicon? Anything else than this CCH thing that's actually complicated to make? So we applied a similar approach. And the first question we had is anything simple, maybe not a complex, like just a substitutional and interstitial in silicon. And we did the screening. We're like, we really want that. That's the signature we want. And this is the best we found. And sometimes, that's also nice. This approach can also tell you, yeah, no way to find what you like to have. So you should move on to other solutions. So this is the best. This is iodine on silicon. But you see, the reason I don't like it is if you actually go to, this is electronic, but even if you compute the optical response of this material, of this defect, it's really in the mid-infrared. And you don't want to be there. The fiber, it's not great for fibers, etc. So, okay, what can we do? Then you can start looking and say, okay, actually, there's another option. You can excite from a band to a defect level. That's possible. Is that crazy? It turns out while we're doing that the T center that everybody was using actually has totally that electronic structure. And it makes sense that in silicon, because you have such a small band gap, you might have to rely on these type of defects. That might be the only game in town, and we're still searching for these 2-level systems. We haven't found one yet, despite a lot of search. I'm not going to go in details. They are disadvantages. They tend to be low temperature, because otherwise you break these bond excitons. But in practice, for many applications, anyway, you're going to cool down this thing. So we have a database of around 20,000 charge defects now. Why 20,000? Because they are charged. Why this so many numbers? Linked to your question, Ken. This is also charged. We try different charges, and some of them might be stable and less stable. But at the end, you also look at all substitutional, all interstitial, and we've started making complexes also. So this is basically the TDM, so the intensity, and and there's plenty of options. Again, I'm not saying they're all going to be interesting, but at least it's a starting something to start with. And looking at the data, we found this series of defects that were showing up, and that all kind of had the same electronic structure. So we're pretty excited by that. They were all emitting roughly in between 1 to 750 MeV, which is where you want. We're intrigued. They were all group 3 next to a carbon. And then if you know about the T center looks pretty much similar. And this is a carbon-carbon hydrogen. Now you have a carbon group 3. So it looks like a T center-like. And the reason these are all kinds of the same is because it's driven by the carbon p orbital. So this is a prediction searching in all the data. Can we make some of those? So then the beauty of silicon is there's a lot of data. of silicon. A lot of lines and a lot of papers. Many sometimes don't know exactly what they have, but we found this paper where they talk about aluminum-related defect in silicon. And we believe, because we can compare vibration modes of these defects, we believe this is very likely to be the same defect. So this defect probably had been made in 1988, well before quantum information science was there. Actually, to give you perspective, this is me in 1988. And I want to really thank my dad, who sends me like pictures of me when I was a kid on Messenger, so I could use a professional use of that. So this is a while ago, and recently, because we're excited by this defect, we kind of remade it with my collaborator Jifeng Liu and Archana Raja. We think we have the line, we found the recipe. This is through ion implantation, implant aluminum, and you do annealings, and I think we have it. We're gonna start digging into this. We're talking with collaborators that made it before us. Actually, they had it in their sample without willing, and they started saying, okay, you know, we looked at something. One prediction we made is that these defects, aluminum should be brighter, should have a stronger transition dipole moment than the T center. And so they made measurements, and indeed, at least at this stage, it seems brighter also. So that's a pretty exciting result. This is from Daniel Ingebottom, very good group in Vancouver working on these silicon defects. It's a synthesis workshop. What about synthesis of these things? It's kind of a little obscure. You read papers, it's like ion implantation, annealing, maybe another ion implantation, even some have like boiling of water on the sample. Like you have all kinds of things that you don't really know exactly why they've been doing this. And so typically you have a sample, you do ion implantation, you do some annealings. And something that troubled us is we found the aluminum carbon in the literature. We think that has been made. We even found the gallium carbon. We think that has been made also. But we never found the boron carbon. And if you know silicon, boron is everywhere. I mean, this is a very common dopant. Why does nobody has, I mean, you should have seen the boron carbon. So we started to think about the kinetic for formation. You can come with a very simple picture of how these things form. You basically have some events, it can be irradiation, it can be carbon implantation, that basically move this carbon out of, and then you have an interstitial that's mobile, it diffuses, and it gets captured by some substitutional defect, and hopefully makes your T center. So this is the simple picture of synthesis in there. And so can we use that to understand? With DFT, you can compute these barriers, like people do in chemistry, like you have a barrier. And so we started doing that for the aluminum center, for the gallium center, and it turns out that the boron center has a much higher kinetic barrier. So our hypothesis, it's an hypothesis, is that the reason people haven't seen it, it's because it has much higher barrier energy. Maybe you need a bigger, higher temperature of annealings than what usually people do. But this is to be proven, but that's also, it brings the question of this understanding synthesis of this thing. And this is going to be essential. It's going to become essential. People trying to make device with this. So we'd better understand how they fall. Okay. Previous speaker talked about machine learning and AI. What can we do with AI this? We have a large database of relaxed structure of complex defects, 20,000-ish. And so if you look at what we do in computation, most of the time, a lot of the computational time is just to relax. You propose a structure, and maybe that's not going to be the right structure, and you do some relaxation. And this is the craziest complex defect I can think of. This is thallium fluoride, which I cannot tell you how this thing will relax. This is from DFT. This is the DFT result. You relax, it relaxes to a wacky structure. Can you actually accelerate this by not using DFT, but using what we've done before and learning from that? And this is work with folks from computer science in Rice, Evan Dramko, Chris Germain, and Tazos Kyrilidis. So they're from CS. So they proposed an architecture without going into the details of the AI. It's actually a nice thing of the architecture. It has a transformer. And if you use ChatGPT, the T in ChatGPT is a transformer. That's an architecture linked to neural network that is very efficient at capturing information. And this is what I'm showing here is a comparison between the actual force from DFT, the forces on the atoms that move the atoms in a certain way, and the one you could predict just by learning from, let's say, thousands of previous DFT computation. So we're looking pretty good. To give you a more precise example, this is the relaxation with DFT, and this would be the relaxation we have with our method, which is not that far. We still would like to relax it with DFT afterwards, but it's a much better starting point. So we're going to go much faster now that we've learned from previous data. On that, I'll conclude. If you're interested in this field, we actually got 2 Emers Bulletin review, and they're really nice because I think this one especially is bridging the gap between a community that's trying to do entanglement and doing devices and the community of material scientists. And we sometimes don't really have the same language, and it's good to talk to each other. And then this one is especially in using computation in that field to find new defects. I hope I give you the feel that you can design new defects with computation. I think it's impacting many other fields. Defects are very important. We have a big program on semiconductors where we try to avoid certain defects in semiconductors. And I think I would really emphasize that my experience is that the material design efforts should combine theory and experiment in the same team. And I don't know, like spread that to the funding agency. I think the most successful teams, and this is an example of that, are the ones that work together on that. This is actually the team of PIs and especially of students and postdocs who work very hard on this. These are my students at Dartmouth when I was before and at Rice now. And all these folks have been great to work with. And really want to thank the US Department of Energy for financial support for that work. Thank you.